Hi. Hello everyone. Welcome to information sharing session on failure analysis. Casting defects are rarely unintentional. They happen when certain processes in the manufacturing process aren't properly managed. A defect might be caused by a single, well-defined source or, more commonly, by a mix of causes. Only the most prevalent faults are selected for characterization among the various problems commonly encountered during traditional casting methods such as sand casting, die casting, and investment casting. Shrinkage in casting. Solidification shrinkage occurs as metal transitions from a liquid to a solid, while thermal contraction occurs as it cools to room temperature. Shrinkage in the foundry necessitates careful planning in the pattern and molding design. As a result, shrinkage allowances are built into the design of cast parts to ensure that the desired dimensions are achieved. Shrinkage tolerances for various metals are known, and an expert mold designer will account for shrinkage while creating a mold. Shrinkage can produce defects in cast products, resulting in failure, leakage, and other issues. These faults can sometimes be seen on the casting's surface and can be discovered visually or via die penetrance or other non-destructive methods. Internal casting defects are sometimes difficult to detect and require X-ray inspection or destructive testing. The term, open and closed shrinkage flaws, refers to both types of problems. Open shrinkage defect. Pipes may form in the surface and extend into the body of the casting if the metal cools and shrinks without enough liquid to fill any holes. Cave flaws, also known as sinks, are imperfections that start on the surface and propagate across the face. In both cases, the faults are exposed to the atmosphere, and air replaces the molten metal. Cracks and hot tears typically appear during the final phases of solidification and can be confined around abrupt changes in stress concentration, such as a thin web linking two heavy parts. They can also happen when there isn't enough draught in the portion or when heat pools in heavier sections. Closed shrinkage defects. Closed shrinkage flaws, also known as shrinkage porosity, are imperfections that arise within the casting. Hot spots are formed when isolated pools of liquid form inside hardened metal. The shrinkage defect usually appears at the top of the hot spots. They require a nucleation point, thus contaminants and dissolved gas can cause closed shrinkage flaws. The faults are divided into macroporosity and microporosity, or micro-shrinkage, with macroporosity visible to the naked eye and microporosity not. Causes of shrinkage defect. There are numerous causes of shrinkage defects, including insufficient metal feed, isolated heavy portions, and sudden sectional changes. Failure to achieve desirable heat centers, such as risers or ingates, in terms of directional solidification. Mold enlargement as a result of soft or uneven ramming. An inappropriate metal composition, such as one with a lot of phosphorus or little carbon equivalent. Extreme pouring temperature. Gas defects. Blowholes, surface or subsurface pinholes, intergranular porosity, and other gas defects are frequently seen in castings and are brought on by the creation, buildup, or entrapment air or gas. The riser of the runner top is where gas holes typically appear. Causes of gas defects. Gas defects are typically caused by the sand mixture contains a large amount of moisture, fume, carbonaceous, and gas-producing material, and has poor permeability and grain size distribution. Molds that are not consistently rammed, hard to ram, and insufficiently ventilated. Cores that are poorly permeable, hard, unbaked, and improperly ventilated, as well as overly wet or thick core paste. Ladles that are cold and moist, slow and interrupted pouring, gassy metal, loud stirring, overheating, etc. Using chills and wires that are rusted, inadequately coated, oxidized, and wet. Pinholes. Gas porosity is a type of pinhole defect. They are often small, elongated holes at, or immediately below the casting surface, with the pinholes' long axis perpendicular to the casting surface. Steel pinhole walls are frequently smooth and shiny. When the pinholes extend to the casting's surface, the inside may appear oxidized with a slight dendritic structure. Pinholes can form on or below any casting surface, however they are more common in thin and intermediate transition thicknesses, where reentrant angles can act as hot spots. Pinholes are mostly formed by hydrogen evolution during solidification. Pinholes are also produced by molds with high moisture content, gas-generating components, and metal mold reactions. Improper degassing also contributes to gas porosity. Causes of pinhole defects. The following frequently results in pinhole defects. Too much nitrogen in the melt as a result of the charge composition. The charged materials contain an excessive amount of oxides, hydroxides, rust, and other contaminants. An excessive amount of aluminium in the melt. The melt's manganese and sulfur level is excessive. An excessive amount of nitrogen in the sand. An excessive amount of moisture in the sand. The molding sand produces too little lustrous carbon. The core sand has a very high nitrogen content. Too much nitrogen and hydrogen is present in the core binder. Using too extended passages. There was excessive swirling and slag buildup during pouring. Misrun. When the metal fails to completely fill the mold cavity, a misrun or shortrun results from a lack of process completion. The failure of two metal liquid streams flowing in separate directions to combine causes cold shut, which leaves crack-like indications with smooth rounded edges. Causes of misrun. The following are the causes of these flaws. The metal's insufficient fluidity. The pouring temperature is low. Interrupted pouring, incorrect gate, runner, and sprue sizing, and sections that are thin. Hot tears and cold cracks. Hot tears, cold cracks, warpage, and other faults emerge as the casting cools from solidus temperatures to room temperature. Hot tears are crack-like flaws that occur when the mold is cooling or immediately after solidification. These fissures are quite uneven and have severely oxidized surfaces. Cold cracks are continuous, but hot tears are ragged or uneven. Hot tears are caused by three factors. Internal strains brought on by restricted contraction because of mold or core resistance. Internal stresses brought on by differential cooling because of poor casting design, and high pouring temperature. All of the casting flaws mentioned so far are often found by radiographic analysis. Primary processing defects. Rolling. Ferrous and non-ferrous alloy roll bars are first cast as ingots or billets, and then they are hot rolled into a variety of sizes and shapes. The top, bottom, and areas that are typically prone to flaws like pipes and blowholes are cropped off. However, because of insufficient cropping, some of the flaws may still be retained. These flaws are prone to collapsing and extending in the rolling direction. The majority of these discontinuities, which are often oxide layers, always roll up from the outer surface to any depth. The best method of detection is a micro-examination of a transverse disc that has been sliced at various points along the rolled length. This imperfection is found using an ultrasonic flow detector. It would be possible to avoid this flow by properly cropping the top and bottom ends of the rolled length. Seam. Another typical defect is a seam, which is a discontinuity extending along the direction of rolling at the surface and is often recognized as one of the rolling flaws. It is caused by the folding and rolling of oxidized surfaces. The heat gradient during rolling is likely to cause cracks on the rolled bar surface. Although it is common practice to trim off the ends of rolls that are prone to cracking, residual cracks may remain in the cut ends. The Magnaflux check can simply and precisely detect seams and cracks on the surface or subsurface of steel bars. Visual and/or dye-penetrant checks, followed by light etching, disclose these faults in light alloy bars. Non-metallic inclusions. Chemical substances and non-metals are non-metallic inclusions found in steel and other alloys. They are the result of melting and pouring related chemical reactions, physical consequences, and contamination. These inclusions are divided into endogenous and exogenous groups based on their source. Endogenous inclusions, often referred to as indigenous, develop naturally within the metal as a result of chemistry. These substances are usually quite tiny and precipitate upon cooling. Non-metals become trapped and forming exogenous inclusions. Their origin can include slag, dross, flux byproducts, and mold fragments, and their size varies widely. If the melt is dirty, the ingots produced during rolling will have irregular stringers of inclusions made up of silicates, sulfides, and chains of oxide particles. Magnetic particle examination of steel bars displays these flows as discontinuous straight lines. The intensity and spread of these inclusions are revealed by a succession of step grinding and magnafluxing operations. Straight line signals might not be continuous, however chains of globular oxide particles that are present indicate continuous flow. Not all of these longitudinal inclusions are dangerous, depending on how the product is used in the end. Delamination. It is yet another significant flow on a sheet or plate. Because there are oxide coatings on the surfaces of the large blowholes in the ingot or billet, they level out during rolling and do not weld together. If necessary, the flow can be found by macro-examining the edge following light etching and polishing. In contrast to thin sheets, where it is not practical, thicker sheets and plates are better candidates for ultrasonic inspection. The ingot roll billet must be properly cropped at the top and bottom ends and examined using ultrasonography and macro-etching before the corrective methods used to ensure freedom from the defect are discarded. Exfoliation. Even while it is not a common flow, it still frequently occurs in rolled or extruded goods made from specific aluminium alloys under particular temper conditions. The corrosion fault manifests as thick, powdery corrosion products that attack along the grain boundary which is parallel to the working direction. This causes a leafing effect, when the grain deformation reaches a critical level with regard to grain size versus width, especially if the materials handled are in the T4 or T6 state. This fault is prone to increase. It is practical to conduct an ultrasonic inspection check to identify the beginning of exfoliation cracking. This deformity is fairly simple to spot visually or with a 10 times magnifier thanks to the presence of its distinctive traits. Micro-examination will, nevertheless, demonstrate the exfoliation's presence. Aluminum, copper or aluminium zinc magnesium alloys are heat-treated in the T73 condition, or the double aging procedure, to get around this. In next session, we will go through forging process defects. Thank you.